Hello, this is day 12 of chapter 12, sequences and series, and this is sigma notation, or summations. And what sigma is the Greek letter that looks like that. It's a funny looking E, or a sinister looking M if it's sideways, something like that. But there are also some other things that go along with this, like N on the bottom. This tells you it's kind of like in terms of a sequence, and it tells you where you're starting. And then K at the top tells you where you're ending. And then A sub n right here, that's just the expression of some general term. So there'll be some formula there or whatever, some explicit formula. But overall, this whole thing, it just tells us that we're adding up a whole bunch of things. And when you add up a whole bunch of things, it's called a sum. And that's why this is called a summation. Summation. All right, so here's a typical problem. Sometimes it's written like this. You may see, B equals 4 on the bottom and then a 7 on top. Or it could be written on the side like this. Just depends on whatever program you're using or whatever you see. But then in parentheses is the general formula. And so you see where B is. There's only one variable, and that's where you're plugging in. But B is starting at 4. So we're going to write the expression in expanded form and then find the sum. Basically, just generate the terms of this sequence and then add them all up. So kind of like making a series. Anyway, 3 to the b plus 1, we're plugging in 4 first. So 3 to the 4th plus 1. That's your first term. And then it's a summation, so we're adding. The second term then would be 3 to the 5th plus 1. It just goes up incrementally by 1. Right, so 4, we wrote that part, and then now we have to write where b is 5. Increment by 1, and then to the 6th. So it incremented by 1, and then to the 7th. And then we stop there because that's the ending value. We stop at 7. So we just need to calculate what each of, just basically simplify this expression. I wrote it in expanded form, and is equal to this. So 3 to the 4th is 81, plus 1 is 82. 3 to the 5th is 243, plus 1 is 244. 3 to the 6th is 729, plus 1 is 730. And 3 to the 7th is 2187 plus 1. So 2188, and then we have to add them all up, and then we have to find the sum. If I typed it all right, then I got 3244. 3,244 is what that summation is equivalent to. So this is really not too bad. The notation looks really scary right away, but it's used in stats a lot, the sigma. But really, it's just generating terms of the sequence and then adding them up, which in effect is kind of like a series. So here's some more practice. It's a little bit easier, I think, but we have a larger number, and there's more numbers to generate. So you could pause it and try to do this one on your own, and I'll just start writing. So I'm starting to plug in, 7, 8, 9, and now 10. I have to go down here, 4 to 11, and 4 times 12. So these are all of the terms, and this is a little tedious because we're writing in an expanded notation. We couldn't really speed this process up anyway yet, but we will get a chance to do that soon. So I'm just going to simplify piece by piece and then add them up. So this is 28 minus 1 is 27. 32 minus 1 is 31. And you can kind of see this pattern here in a second, right? 4 times 9 is 36, minus 1 is 35. And look at the numbers I'm generating here in red. 27 plus 4 is 31, plus 4 is 35. So I could just, I mean, I know what each of these little parentheses are going to add up to. I mean, I add 4 to 35, I get 39. That's the same as 4 times 10 minus 1, it's 39. So if I see that pattern, I'm just going to streamline this process a little bit quicker. Plus 4 would be 43, plus 4 would be 47. And I'm just adding up all these to get the summation. 27 plus 31 plus 35 plus 39 plus 43 plus 47. 222. Neat. There's a couple more examples. This one looks a little bit nicer, and there's a kind of a nice thing that happens with this one. First of all, we want to recognize that it's starting at the first term. It's a first term, so n is like 1, and our last term is 4, so it's just the first 4 terms. So this is, we actually start at 1 this time. And this almost looks like a geometric explicit formula, like where a sub n is 2 times 1/3, there's our r, and then to the n minus 1 power. This one, though, is at n. It's not n minus 1. So can't necessarily just jump to this and use a summation, a geometric series formula, because we'll be off by a term. But we'll see what happens anyway. So it's 2 times 1/3 to the first power, plus 2 times 1/3 to the second power, plus 2 times 1/3 to the third power, plus 2 times 1/3 to the fourth power, and we would stop right there. We could, well, here's the brute force way of doing it. This would be 2/3. Just by calculating it all out, this would be 2/9. 1/3 squared is 1/9, and then I have a 2 on top. And you know, this is going to be the same thing. It's going to be 2. You can see there's just a power of 3 happening on the bottom. 27, 2 over 81. All right, that's totally doable. We could put that in a calculator and do it. I'm going to try and just expand our minds a minute and see if we can make a relation to something that we've done before. In effect, this is my first term, and this is my last term. Whether it's called the first, you know, n equals 1 or not, this for our intents and purposes is the first term. But it doesn't look like a geometric series yet, because our first term should just be 2. Alternatively, we know what r is. It's 1/3, and you know, this appears to be my first term in the actual sequence I did. It appears to be the last term, the fourth term. So if I just use 2/3 as my a sub 1, and then r is 1/3, that would be my formula, my actual formula for it, but I'm doing a series. So this would be s sub 4 equals 2/3, 1 minus 1/3 to the fourth power over 1 minus 1/3. Now, in an effort to make this more simple, it actually looks way more complex. But just keep in mind that we can relate to anything if we recognize some type of a series or sequence in this summation. We can use those formulas because it's literally the same thing that we're talking about. We're adding up terms of a sequence, and it happens to be a geometric sequence. So as long as I know that I have a first term, and I know how many terms, I could use the series formula. At this point, though, I would suggest probably just adding up these terms, because it's going to be the same amount of work to put into a calculator. So 2 divided by 3 plus 2/9 plus 2/27 plus 2 divided by 81. I would say, hey, you know, we should really be able to like add up these fractions, because you know we've gone through a ton of math. We should be able to do this, but that's not what we're learning. Ultimately, I get 80 over 81. I change it to a fraction to check that out. So neat, I get 80 over 81. A couple more examples. All right, sigma notation again, starting at 6, going up to 10. -1. Something interesting is going to happen here. Times by 2 times by 6 plus 3. All right. That's just one term right there. So I'll color code the next term, I guess. Plus, summation is always adding. If you have 1 to the 7th, 2 times 7 plus 3. Negative 1 to the 8th, 2 times 8 plus 3. Negative 1 to the 9th, 2 times 9 plus 3. Negative 1 to the 10th, 2 times 10 plus 3. Okay. So we have each of these terms. We should notice something right away. Anytime we have a negative number in parentheses raised to the incrementer, I don't know if that's a word, but the number that we incrementally add by 1 to generate the sequence, that means that it's going to go from even to odd to even to odd, and that's important because it's a negative number. Negative number to an even power is a positive. Negative number to an odd power is a negative. So in effect, each of these terms of the sequence are going to alternate their signs. I'll be adding a positive number, and then adding a negative number, and then a positive number, and then a negative number. So just keep in mind anytime you see that. So this first term turns into, I need a different color. This would be just a positive 1. Negative 1 to the 6 is just 1. 2 times 6 is 12, plus 3 is 15. And then I know this term is going to be negative now because a negative 1 to the 7th is a negative 1. So whatever I get, it's going to be my negative. 14 plus 3, 17. And then positive, negative 1 to the 8th is 1. 16 plus 3 is 19. And hopefully we can kind of see a pattern here. There's only 2 more terms we could continue to generate, but the next term is going to be a negative, and it looks like they're just going differing by 2 each time. So minus 21 and then plus 23. So that works. And we can just add them all up. So, I mean, this will be interesting. 5 and negative 17 gives you a negative 2. And then I add that to 19 is going to give me a 17 because it's a negative 2 I have. And then minus 21 is going to be a negative 4. And then add that to 23, and I get a 19. You can just put into calculator as well. All right. These next 3 are asking us to write this in sigma notation. So we need to know what an explicit. We need to write this as an explicit form of a sequence, knowing that it's like really a series, but we need to like write it as a sequence formula and know how many terms we're adding up. This is obviously the first term. This is when n is 1. We need to know what n this is so we know where to stop. There's sigma. We would say that, from n is 1, but then we need to know this top number, whatever that is. All right, so we could figure out a couple things. First of all, this is an arithmetic sequence. Your a sub 1 is 16. We know d is 3 because they're going up by 3 each time. So we could have the formula a sub n is 16 plus 3 times n minus 1. All right, but I need to know where I stop. I need to know what n that is. So we can figure out n by saying 61 is 16 plus 3 times n minus 1. Now just solve for n. So this is a basic problem from day 1, I believe. I'll subtract 16. See where we're at. That brings you down to 45. And we could divide by 3. 15 equals n minus 1. Add 1. 16. So this is the 16th term. So this sigma, start at 1, go to 16, and we have this formula. We already have the formula because we wrote it. That's the formula that generates this sequence. You can choose to simplify it, just to say that 3 could be distributed right there, and that would look like 16 plus 3n minus 3. And it just kind of cleans it up a little bit because 16 and negative 3 can be added together. This would be 3n plus 13. And you can tell that this would work as if I generated this first number in the sequence, I should get 16, plug in 1, 3 times 1 is 3, plus 13 is 16. So this would be good. This is also acceptable, it's just not completely, it's nicer looking if you simplify everything. Same situation here. We should figure out just what the formula is. Looks like it's geometric. Your first term is 1. Your next term, or R value then, looks like it's just being multiplied by 3 each time. So a sub n is 1 times 3 to the n minus 1 power. And I can see which term this is. This is a sub 5. So this one's a little easier in that n would be starting at 1, going up to 5 terms. And then my formula. 1 times 3 to the n minus 1 is just as easily written as 3 to the n minus 1. That was a fast one. All right, last one. Can we do it? How bad are you? Bad. All right, first term is 4. Second term is 16, then 64, then 256. So if you're not sure what's happening here, it's not arithmetic. They're jumping up not by the same amount. You could figure out by doing 16 divided by 4 or 64 divided by 16. Either way, R is going to be 4. We have the first term right there, and we have the fifth term right there. So we know this already. We can do this part right here without knowing anything about the type of sequence. Okay, so that's just like that's how we write sigma notation or summation. All right, and then the rest of this is geometric, so it's a sub n equals first term is 4, R happens to be 4 as well, to the n minus 1 power. And we can't simplify that in any way, so we can just write it as 4 times 4 to the n minus 1. All right. And there's one little tip here at the for number 23 on the homework, where k exclamation point is a factorial. So if you were to plug in, so 5, for instance, 5 factorial is 5 times 4 times 3 times 2 times 1. That's what a factorial means. So your first number you plug in is a 3 factorial. That first term is just 3 times 2 times 1. Your next term when you plug in 4 is then 4 times 3 times 2 times 1, and so on. All right, hope this helps. This is sigma notation. Good luck.